Yes.
I want to report about research we did in Dresden on the complexity of finding good proofs. So if we ask human what is a good proof, the answer may be not very clear. So either you can say that this axiom is, so what you want to derive is an axiom, so why is the sky blue? Because it is. Or you can elaborate it a bit more and give a fuller answer. Or you can write a research article about it using more complicated terms, using physics, chemistry. So even in a human scenario, our goodness of a proof may depend on context and also not very simple to define. So same holds for formal proofs. If we have a theory in some description logic, we have an axiom which is entailed by this theory, and we want to see a good proof. For that, we need, first of all, understand what is a proof. Then we need something which can derive all possible proofs, what we want to consider. In human scenario, you can consider brain as a deriver, or for description logic, it can be the reasoner. And define what good means, measure for goodness. So to consider these 3 points, first of all, we assume in our research that proofs are direct labeled hypergraphs. Here, blue boxes represents hyperedges. And we have a deriver which generates all possible proofs, and a good proof is part of the output of this deriver. Here we limit the set of deriver to one which output is polynomially bounded with the size of theory, T-box, and axiom. So as an example, practical example, you may consider ELK for EL, which is output of the reasoner is polynomially bounded for concept subsumption. And to measure goodness, so we considered several measuring functions. So for example, you can say that proof is as hard as its hardest axiom, or you want to sum all axiom complexities which are part of the proof, or you may consider also proofs which have tree-shaped. That is quite common for classical formal proof representation. Or also you can consider some properties of the proofs because they are also graphs. So you can consider depth, force path, and try to optimize it. So you'll want to find a good proof with minimal weight, with minimum measure of this proof will be small, or as small as possible. So we categorize this measure into 2 classes. So we define 2 classes of structural measures. So psi measure should be computable in polynomial time. We wanted to find tractable results, first of all. And that's why we concentrated on polynomial time measuring functions. And every subproof. So if we want to consider proofs which were derived by removing vertices or by merging them, the weight, the measure of the new proof should not increase. So it is also quite intuitive notion if you consider vertex size as a measuring function. So if you remove some vertices, proof shouldn't be more complicated to understand. Also consider specialization, local psi measures. So if you substitute a part of the proof with something which weigh less or greater, so as a resulted proof will also weigh less or greater. So it's monotonic for all operators. And we show that problems of finding optimal proofs with respect to psi measure will be NP-complete, and for local psi measures is P-complete. So what it means for the list of the measures which I showed before, it means that these measures, hardest axioms, hardest inferences, if you consider proofs which are trees and some axiom complexities or some inference step complexities, these problems will be P-complete for the polynomial size deriver. But if you consider more generic for generic hypergraphs, not necessarily trees, or classical problem justification size, we confirm it is in P-complete. The last two options, depth first plus with trees, are not psi measures. That's why we didn't prove NP completeness for them yet. It's still future work. So if you're interested in this topic and related, please stay in this session to listen to the next DL talk. In this DL talk, we will report about user study when we try to understand which measures are actually valuable for users. And on Monday, X-Locker talk, Patrick will report about practical aspects of proof generation and implementation we did in Dresden. Thank you.